Okay, so what I wanted to talk about today in this talk is about this kind of big project we had in which we had to test a lot of documents that describe protocol behavior for basically for Microsoft protocols. So these are some general stats of the project. So on one hand, I'm just going to go briefly through the main key points of this project. On the other hand, it's a very good example where model-based testing was successfully used. So I will try to convince you that model-based testing is a really efficient approach for a reasonable class of testing problems. So this talk is going to be about model-based testing, the concept, and also about Spec Explorer, the tool that we used for this particular project. So the main points here that I think it's worth mentioning is that for this project we ramped up hundreds of engineers that they were mostly fresh out of college. So these people may have general knowledge about protocols, but not about specific protocols. So we also had to design a project that scales well for this big amount of protocols. And as a result of this project, we found a lot of document bugs that hopefully made your life easier when you had to deal with these Microsoft protocols. So the main idea of this is that we started with a technical document, and through some formalization process, we end up with test suites. So what we're interested in testing is, on one hand, we wanted to validate the consistency of a technical document. So for example, we're interested in cases where the document says, well, under these circumstances, you should send message A, and later on it says, under these same circumstances, you don't need to send message A. So that's one of the problems that we wanted to detect in our documents. And the other thing about this process is that we had to simulate aspects of an implementation process. So we tested both server and clients. So for example, when we test a server, basically the test suites had to act as a client that stimulates the server. So there were aspects of an implementation process that we had to deal with. So our technical documents, if you're not familiar with those, are kind of RFCs on asteroids. So basically we have must, may, and should, capital must, may, and should as requirements in the document. So from the technical document, we could extract a set of normative statements, and through this formalization process, we transformed these normative statements into assertions that were checked mainly against Windows implementation. But one thing we were interested here was we wanted these test suites to be portable. So we did these checks against Windows, but we wanted these test suites to be portable, and so you can use them against any implementation of the same protocol. So, as I said before, this project was mainly carried out by vendors. Vendors were not protocol experts, and we used what we call a clean room approach. So from the technical document, and just by that, vendors had to extract these requirements in order to formalize a test suite. So this was the only contact vendors had with the protocol, and requirements were not constructed from some private talks with the developers of the protocol. So there were not real contact with those people. It was just about what the document says. And the other point, and I think it's important, is recall that this was about testing the documents and not the implementation. So, and this is kind of weird if you think it from the testing point of view. When we found a bug, that usually almost meant that the document was wrong and not that the product was wrong. we were testing documents. So the first step of this, and this was a manual step, is that we transform all the requirements, the must, should, and may that we found in the document, into this spreadsheet, into this requirement spec. I think that later this changed to kind of a fancy database, but when I worked with this, it was just a plain spreadsheet. So each requirement had a number assigned, and in order to track that requirement across the whole process, we included those requirements ID in the model we generated. I'm going to talk about this later. What is this model? Those IDs were carried over the test suites that were generated, were logged in our logs when we execute those test suites, and we also inserted some beacon packets when we generate captures, basically decorating the capture with the same strings that we found in the document. So at this last point we use netmon, and so if you look at the capture we generate in netmon, you can find these beacon packets splitting the traffic, saying, okay, now one validated this requirement, now one validated this requirement. So in that sense we could track all the requirements from top to the down of this whole process. So now I'm going to briefly describe what model-based testing is. And if you look back, this is the part where model-based testing was used. So extracting requirements is usually a manual step, but this is what changes from traditional to model-based testing. So this model building stage and this test suite generation step. So we started with requirements. From requirements, we build a model, and this is usually the hardest part, and the hardest part to teach also. And it's mainly about abstraction and design. So what you are interested about is just in modeling the testing behavior you are interested about. You're not testing your whole system. Perhaps you're just testing one part of your system. So just by building the model, you also get some feedback, right? So you can find that the model is contradictory at some point. You can find that the context where a requirement must be asserted is not clear. So by this process in which you formalize what are requirements into a formal model, you get a lot of early feedback. And that's usually good. That's something that if you get it later, it can be a problem. So just by building that, you get a lot of things back. So from the model, we generate a bunch of test cases, and this is where model-based testing pays the most, is when you automatically generate, you have a push button and say, okay, generate test cases. So test cases basically define which are the input sequences that will drive the implementation through the path you're interested about, and it also generates what is the expected outputs. So you can observe the implementation using this as a test oracle. So at the end, you finally get a verdict. So each of the generated test cases, when you run them, it can be right or wrong. So this can mean that, well, if you get that the test case failed, it's because the implementation is wrong, but also it can be that your model is wrong, that's just some piece of software, so it may have bugs, or that your requirements are wrong, right? Which, I mean, in our particular case, basically this part of the graph is the one that we're interested about, because we're not testing the implementation, we're testing our documents, right? So the main thing we've learned from this project is that this is represented like the traditional way for testing a system. So basically you work first on the spec, then, and I'm going to talk about this later, you design your test cases, you code them, you run them. This represents what we did. So look that using model-based testing, there is this new stage called modeling that is not present in the traditional way. And basically, what we proved is that in this kind of big project, we saved 40% of effort. So at the end, we saved hundreds of hours just by using model-based testing instead of traditional testing. And in fact, we ran all this data through a group in Microsoft Research, and they validated that all the data we have is statistically significant. So doing model-based testing, in our case, really saved us a lot of time. So it's really more efficient. So let's look at how traditional test design looks like. So you start from some feature spec and you derive requirements from that. That's the usual case. So from that requirement, you have a lot of testers that generate test cases. Thanks. And this is a manual process, right? So the tester looks at some requirement list and says, okay, I'm going to test what happens under these circumstances. So I'm going to code that. As a result, you get usually a lot of different implementations, and this is even worse if the tester group is big, right? In which probably there are a lot of code and a lot of replication in some sense. So on one hand, one of the problems, and these problems are even worse when you scale up the project, is redundancy, right? Probably the test case that tests the first field of some message of some protocol is very similar to the code that tests another field of that same message. And if that was written by different people, you would have very good chances to end up with duplicated code. The other thing is that, well, how far I should go with test cases, how many test cases I should code. Well, this usually depends a lot on the team. So a tester may decide that he needs to generate a bunch of test cases, but another tester could end up deciding another thing. So that's something that we didn't want to have, because we want to have a consistent replication related to protocols. So different test groups should come up with the same testing for a document protocol. So on the other hand, with model-based testing, this process is the same. So you start with a feature and you manually identify requirements. So that doesn't change. But what you do in this step is that you generate a model of how your system should behave in terms of the stimulus you define. And from that model, you have this push button thing that you can automatically generate a lot of test cases, and as many test cases as you want, in fact. So once you have the model, I can ask you, okay, so tell me, how many test cases do you want? And I just move the dial and push the button, right? And on the other hand, it's much easier to come up with just one implementation. So usually, and again, I'm going to describe this in more detail later, you can split your implementation in two, in which you agree on some common higher level interface where test cases interacts with that, and you can just code a general library on the other side that basically translate those test cases into on-the-wire. The other thing, and this is something we found is as important as writing your test cases from scratch, is how you maintain a test case. So this project, we started this back, I think it was later back Vista, then we have to update some test cases for Windows 2008 and then for Windows 7. So we really had to do a lot of updates from a lot of protocols. So usually this from the traditional test approach is really complicated. You first need to identify which requirements change, right? But then you will need to say, okay, so how many test cases were related to that requirement? And you need to go and modify those test cases. And if you have a lot of replication in code, this is really difficult. So from the model-based testing point of view, you again have to identify which requirements change. That is the same. It's again a manual process. But Once you do that, the only thing that you have to do is change the model. And again, I mean, this requires work. But at the end, it's much easier to change the model than to change independent test cases. And let's say that a rule of thumb is that if you did a one-line change in your protocol, that ideally should be reflected in a one-line change in your model. So at the end, it's much easier. Once you have your model changed, you just regenerate your test cases, and you're done. So overall, the value of modeling, the values that we found on modeling, resulted in a reasonably big amount of productivity gain. And the other thing is that no formal methods background were really required for these vendors. So, of course, I mean, it's not that the ramp-up time is very, very short. I mean, it's something that you have to consider. But overall, you don't need years of experience to use model-based testing for these kind of projects. So for the adapter part that I mentioned before, and this is something that was really good in terms of results for us, and something that I recommend doing, is that you can split your process in two, and you would say, okay, I will define an adapter interface, and I'm going to have the test experts work on the upper part of this diagram. So they're going to design test cases, and they're just going to invoke this common library of functions that will just translate those tests into on-the-wire messages. So this other part of the team, they don't need to be testers, right? It's just an engineering work in which, from an agreed higher level interface, they just transform that into real packets. And here, we can abstract a lot of things like different server setups, different configurations. So, for example, if the test cases, I don't want the test cases to be affected by the transport, for example, of a protocol. Well, that's probably something that I can just push down to the adapter implementation. I can have a config there and say, okay, I'm running on TCP or I'm running on UDP, and the test team doesn't need to be aware of that. So usually this is a very good way to split the work. The other thing, and in terms of the process, is, so you start with a protocol. You first have to understand what you're talking about. So you first understand the protocol. From that, what you define is the very basic actions. There is this higher level interface that I've talked about. And in the case of a protocol, this usually is what messages you send across the wire. So if you're testing some specific protocols, sending message A, expecting message B, sending message C, those things usually define which are the actions that the test cases execute on the implementation. So once the actions are defined, that is like the common contract between these two parts, then you can have completely independent teams working on that. So the team that works on this side doesn't need to wait for the model to be complete. This can be done in parallel. So this team, from the adapter definition, is going to implement those adaptions to translate to on-the-wire. And the other team is going to define the model, explore the model, convince themselves that the model is what they really have in their minds. From that, generate test cases that will use these adapters to actually execute an implementation. So this side of the diagram is the testing expert team. This side of the diagram, we don't need tester here. It's just like a regular implementation work. So now I'm going to go more into Spec Explorer, the tool that we used for doing model-based testing. So this is the general look and feel of the tool. So you write your model. right? And later I'm going to give more details about what does it mean to run your model. But from your model, you can say, okay, I want to explore it. And what you get is this nice diagram in which you have states and edges connecting the states representing how the model behaves. So this is usually an iterative process. So you start with some model, you explore it, you look and say, no, I mean, this protocol shouldn't be doing this. Is that I'm not understanding the protocol? Is a bug on the protocol? Our experience is that usually it's a bug on the model. I mean, it's a piece of software, so it can have bugs. So you analyze what's going on, you go back to your model, you change, you fix what you think should be changed, and you iterate this until you are convinced that your model kind of represents what you have in your head. So once that you have your model and you are confident of that, you generate these cases, and again, this is like a push button, right? What you get is a bunch of test cases. This is generated code, so you don't need Spec Explorer to run those test cases once they are generated. I can generate these test cases and I can give them to you and say, hey, run this against your product and see if your product behaves as the document says. So all this thing is based on .NET, so you can use whatever .NET compatible language you like. So you can write your model on C#, but you can also use Visual Basic, whatever language you like the most. So once you have your test cases, you can execute them and see the results. You are going to be using your model as the oracle, and you're going to be testing that against your implementation. So overall, your model is basically a state-oriented description, right? In which you have a bunch of object-oriented entities that represent the state of your model, and you have what we call rules. Rules are basically the stimulus that your system allows you to do at a higher level, right? And that's something that you usually have to design. So the idea is that rules define how your model transitions from one state to the other. And so the diagram that I showed before was basically showing states and edges. So the edges, you can think of that as traversals of those rules, right? The nice thing about Spec Explorer is that you can describe in a descriptive way when rules are enabled. So you can say, okay, let's say that my system starts at this state, and you define variables and that basically summarize how your system starts. And then you say, okay, so I have this bunch of rules, but it's not true that all these rules are enabled at the start time. If you're modeling a protocol, probably the first thing that you would like to say is, okay, the first thing that happens is that someone requests for opening a file. That's an allowed message that can happen at the beginning. So the rule that represents that, you'd want that to be enabled. So we have a way to express that kind of restrictions in a descriptive way. It's not an imperative way. So you can just say, okay, so the receive request rule is going to be enabled when these conditions occur, right? So taking this to the protocol domain, how many of you have heard about section 3.1 of a technical document? This is the section in where the abstract data model of the protocol is described. And an abstract data model is usually a bunch of objects that carry state. And again, this is a technical document, so it's not that it's telling you that those variables should be present in the implementation of your protocol. It's just like an operational description of what should happen. So your implementation should behave as if those variables were there, and the rules that you defined should interact with those variables in the proper way. So looking at this specific section of the TD and using model-based testing for the protocol case, the TD naturally defines a map between the abstract data model and the model of your system that you are specifying. So usually, whatever you find in the abstract data model, I mean, a good rule of thumb is, well, probably I need those things in the definition of the state for my model. And in terms of rules, usually the messages, protocol messages, define the rules of your model. Because for a protocol, the way to interact with a system is just by sending and waiting for messages. So when you hit the Explore button in Spec Explorer, this is the kind of thing that you get. This is the result of exploring your model program. So, as I said before, each of these states represent valid states of your system, of the system under test, and each of the edges represent a transition in the state. So, for example, you start from L0 and you get a logon request, right? Well, so that takes your system to a new state in which that event was received. So if you look, there are two types of nodes. We have these round nodes and these diamond nodes. So in Spec Explorer, this means that round nodes are stimulus that you perform on the system. So usually if you are testing a server, and a stimulus is to send a request. And that's something that I do explicitly. The diamond nodes, on the other hand, are system responses. So it's not something that I control. It's something that I validate. So I check that it's an expected response, but I don't have a real control of that. I can have non-determinism here because the system can respond in more than one valid way. So if you look at that, these type of diagrams, they're called action machines. It's like a more powerful notion than label transition systems because it distinguishes between what is a stimulus and what is a response. And the difference is that if you look at the model and the system under test, so let's say that the model generates this stimulus. This is an explicit thing. It's testing that sending broadcast is possible. Well, that's something in terms of conformance that the system under test should allow. So if we start from the initial state in both systems, whenever I do a stimulus, that's something that should be valid on the other side, right? But it can be the case that the system under test also allows other types of stimulus, but for this particular test, I'm not interested in that. I'm just testing that part. But in terms of conformance, this is something that could be allowed, but I'm not detecting that from the testing point of view. On the other hand, when the system responds, this is a concrete execution, right? So when these two things were sent, I got a concrete response from the system. This is what the system answered. From the conformance notion point of view, my model should allow that edge, but at the same time, it should allow all the possible responses that the system could make at that point. So in terms of conformance, you see how stimulus and responses are not the same, right? In terms of a stimulus, I always do a concrete thing on the model. From the system point of view, I can have more than one valid stimulus, and the other way around for responses. The system will always answer a concrete response, but from the model point of view, I have to contemplate the fact that more than one response is available. So that is for the model description part. So that is how I model my system. The other thing that Spec Explorer offers, which I think is a really cool feature, is that we can combine these state-oriented models with behavioral descriptions that basically allows us to define scenarios that we're interested in testing. So one of the main problems is that, let's say that you are encoding a very complex protocol with a lot of rules, a lot of state, a lot of interactions. Probably when you hit the generate model, you will find a huge diagram that will be really hard to understand. Think that that diagram represents all the possible state of the system, all the possible interactions. So usually for a complex protocol, you get a very, very big diagram. That means that on one hand, you can have performance problems. You'll have to wait a lot for get that result. And on the other hand is that, and this is almost, and this is very important for the protocol domain, that is, usually what you get is an infinite diagram. Usually the result of exploring your model is not a finite diagram, because the protocol is always willing to accept more packets and to respond back. So it's really, really easy to come out with an infinite diagram. So these scenarios are a way we offer to restrict that big diagram into a family of concrete paths that we are particularly interested about. So for example, one way of representing this scenario could be the following. I'm modeling this protocol that deals with files. It can be SMB or whatever. And so I can write this thing as a scenario. I will start with a file open. I will do a bunch of reads. Now I don't know how many. And I will do a file close. So of course, this is not the only thing that the protocol allows. The protocol is much bigger. It has a lot of messages, a lot of interactions. But now I'm just interested in seeing these kind of traces. And observe that this is a very high-level thing because I didn't specify parameters here, right? I didn't say how many file reads I want. It's just about this like high-level scenario that describes what I want. So if you think about that, these kind of things can also be thought of as action machines. I start from the initial node when I do the file open. I go to the file read node, and there I have a loop because I can do as many file reads as I want. And then I go to another node that represents the file close. So now I have another action machine. So what Spec Explorer allows is to compose these two action machines together. On one hand, I have the model program, that is the whole thing, the big thing. On the other hand, I have these scenarios, these kind of things, that represent usually very tiny models. And I can put these two things together and combine them and get as a result a restricted exploration that has all the details and concrete parameters that the model program provides, but is sliced through these simple scenarios. So this is a very good way to get finite models and also models that I can understand. It's also a very good way to understand if the model is really representing what I have in my head. Because let's say that I modeled S and B, and then I say, well, I should be able to do file open, a bunch of reads, and a file close. So if I combine these two things, and the outcome is an empty diagram, that's telling me that the model program is not allowing me to do this kind of interactions. So what's wrong? It's that I did some mistake here when I modeled the program, is that the protocol is not really allowing this. So this kind of scenarios allows me to understand what's going on and to validate that the model program that I have is something that clearly represents what the protocol is doing. So when I have the model program ready and I'm confident that that is what I want, the next thing is to generate test cases. So you have another push button in Spec Explorer that say generate test cases from this exploration, and what you get is a test suite that is basically a traversal of that diagram. So it's a bunch of traversals of not necessarily the model program, but some traversal. I can have the model program, I combine that with a scenario, I get the restricted exploration, and I can generate test cases from that. So what I have is a bunch of things that represent possible traversals that will stimulate the system under test in the way I plan to. And observe that, well, this diagram I put here, they're all linear, but that it's not necessarily the case. When you have these kind of diamonds, when you have non-determinism, you can also have these trees that represent, okay, I stimulate the system in this way, but all these things can happen. So from the testing point of view, I should allow all those things to happen because they're all valid. So just to end with the presentation, the Spec Explorer is now a power tool of Visual Studio. It's free, so if you have Visual Studio, you can download it and test it. This is the link where you can find that. From here, you can also find a lot of interesting documentation that if you're interested, you can probably take a look at. There is an MSDN site with all these docs. And there's also a very nice course on Channel 9. I think it's about 6 or 7 hours course. So, I mean, I don't recommend doing that in a row. I mean, but it's a very high-level course, but it gives all the very basic concepts of model-based testing. So I would really recommend taking a look at that if you're interested in trying this out. Okay, so that was all. Questions?
Thanks, Serge.
Okay.
And
Thank you.
I